Questions 11 through 20 on the 2005 Grade 12 AMC 12A. How many three-digit numbers satisfy the property that the middle digit is the average of the first and the last digits? We have a three-digit number, A, B, C. And they're saying that the middle digit, which is B, is the average of the other two, like that. So therefore 2B is equal to A plus C. And now we just have to make tables and see what we get. So let's start. And let's start with A. A cannot be 0 because if A was 0, this would not be a three-digit number. So we can start with 1. That's the lowest value A can have. If A is 1, let's see what happens when B is 0. C would have to be -1. And that's obviously not going to work because C has to be a digit from 0 to 9. So that's no good. How about 1 and then 1 for B? Well, C would have to be 1. A equals 1, B equals 2, C would be 3. A equals 1, B equals 3, C is 5. A equals 1, B equals 4, 7 for C, 1, 5, and then 9. And then 1, 6 would have to give you 11 for C. And that doesn't work, right? Because C has to be a single digit. So for A, we got 5 values when A is 1. All right, let's keep going here. We're not going to do all of them. We're just going to get some sort of an understanding, and then we can extrapolate that. Now let's start with A equals 2. When B is 0, that means C is -2. Well, that's no good. When A is 2, B is 1, we got 0. 2, 2, and 2, that works. 2, 3, and 4, all according to this formula. 2, 4, and 6, 2, 5, and 8. But then 2, 6, and 10, that doesn't work because, as previously stated. So for A equals 2, we've got another 5. And in a very similar way, you can show that for A equals 1, 2, 3, all the way up till 9, each of those will give 5 possible arrangements for A, B, and C. So we have 9 times 5, which is 45 in total. So number 11, the answer is E. A line passes through 1, 1, and 100 and 1000. How many other points with integer coordinates are on the line and strictly between A and B? So any line is of the form y is equal to mx plus b. And since we have 2 points on this line, we can solve for m and b. So using 1, 1, we get 1 is equal to m plus b. And using 100 and 1000, we get 1000 is equal to 100m plus b. From the first one, we can isolate for either variable, 1 minus b equals m, for example, and then we can substitute that into here. So we get 1000 is equal to 100, 1 minus b plus b, and you get 1000 is equal to 100 minus 100b plus b, and then we got 900 is equal to 99b, and therefore b is equal to 900 over -99, and this reduces to -100 over 11. And therefore, if we go back here, m would be equal to 1 minus b, and that is 1 minus 100 over 11, like that. And this would basically give you 111 over 11 for m. So our equation is 111 over 11x plus -100 over 11. That is the equation of our line. Now we are told that we want to find integer values for this equation. All right, let's see how we can proceed here. So we have y is equal to 111x minus 100 all over 11. what I'm going to do is I'm going to split up the 111 into 11x and 100x, and that will allow me to factor. This will now become 11x, factor out the 100, and I'll get x minus 1 all over 11. Now, I think it'll be much easier to explain how to get integer values out of this equation. 11x over 11, correct? Like that. Plus 100 x minus 1 over 11. Well, this just reduces to x, and now we have this 100 x minus 1 over 11, like that, right? So no matter what you put in for x is not, this part is always going to be an integer. So what we have to really concentrate on is this part. When is that going to be an integer? It will be an integer when x minus 1 is divisible by 11, correct? So we have to figure out all the values of x minus 1 that are divisible by 11. Well, that happens when x is equal to 12, 23, 34, 45, 56, 67, 78, 89, and I think that's it, because we have a range from 1 to, I think from 2 to 99, I believe, is our values for x, because 1 is already taken, and so is 100, right? If you go back, 1 is already taken, and so is 100, and they want strictly between those two. So 2 to 99. So between 2 and 99, these are the only values that give an integer. When you break it up into this form, it makes it much easier. If it's still in some other form, it'll be much more difficult. Like, for example, here, it'll be much more difficult to figure out integer values. But here, it makes it much easier. So how many values did I get? 1, 2, 3, 4, 5, 6, 7, 8. So I got 8, and each of those will give an integer value for y. So number 12, the answer is D. In the five-sided star shown, the letters A, B, C, D are replaced by the numbers 3, 5, 6, 7, and 9, although not necessarily in that order. The sums of the numbers at the ends of the line segments A, B, B, C, C, D, E, and EA form arithmetic sequence, although not necessarily in that order. What is the middle term of the arithmetic sequence? So what they're doing is they're putting these numbers somewhere. I don't know how they're putting them, so I'm just going to put them like that just to show you what's going on. And they then figure out AB, which is essentially the sum of the numbers. So AB would be 3 plus 7, like that, which is 10. And then they figure out all the other ones. BC, for example, is 7 plus 9, so 16, and so on. And then when they do figure out those 5 sums, they find that those numbers form an arithmetic sequence. And they want you to figure out what is the middle term. All right, well, what is an arithmetic sequence? It's a sequence of the form A plus D, A plus 2D, A plus 3D, A plus 4D, like that. If, for example, if we have 5 terms, and in our example, we have 5 terms. So they're saying that these numbers, C, D, D, E, and EA, will form an arithmetic sequence. All right, fine. How do we figure out the numbers? Well, each of these A, B, B, C, C, D, D, E, and EA consists of 2 numbers, correct? So all of them, if this is 2 numbers, this is 2 numbers, 2, 2, and 2, all of them will consist of 10 numbers that are being added. And what are those 10 numbers? Well, they're right here. It's those 5 twice. So the total sum is going to be 3 plus 5 plus 6 plus 7 plus 9. And each of those was used twice, so I'll multiply by 2. And on the other side, the sum is going to be A plus D plus a plus 2d plus a plus 3d plus a plus 4d, like that. Okay, let's see what we get. Adding this up, we get 5a plus 10d, and the right side we get 60. If you divide through by 5, you get a plus 2d is equal to 12. And that's about as far as we can go. Now what they want in the question is the middle term. Well, the middle term is right here. It's a plus 2d. And that's exactly what we figured out. So that's it. We're done. This question, the number is 13, and the answer is 12, which is choice D. On a standard die, one of the dots is removed at random, with each dot equally likely to be chosen. The die is then rolled. What is the probability that the top face has an odd number of dots? So on a die, the dots are usually of the form 1 dot for 1, obviously, 2 dots for 2. I believe 3 dots are in that form. 4 dots look like that. 5, and then 6, I believe, is like this. So what they're saying is that one of these dots is removed. So how many dots are there, first of all? If you add up all these dots, you get 21 dots. And one of them is removed. And after one is removed, we have to figure out, when you roll the die, what's the probability that the face will show an odd number of dots. Okay, let's start one at a time. Let's say that's the dot that was removed. If that is true, what's the probability? Well, out of the 21 dots, 1 out of 21 chance that that dot is going to be removed. If that dot is removed, then this will have 0 dots. Correct? Right here. So if we roll, what's the probability of getting an odd number of dots on the top face? Well, this will have 0, so that's not going to be odd. This is 2, not odd. This is 3, that's odd. This is 4, not odd. This is 5, that is odd. And this is 6, not odd. So we have, out of the 6 possible faces, 2 of them will be odd. So 2 out of 6 chance. All right? So we'll continue in the same way for all 6 of these. Now let's say this one is where the dot is removed. If that's true, what's the probability? Well, they have 2 dots there. So one of those dots being removed, there's 2 out of 21 probability of that happening, since 2 dots exist there. And if that is correct, there'll be only 1 dot left. So let's see, which one of these will now give you odd? This is 1, that's odd. This will be 1, that's odd. This is 3, that's odd. Nope, odd there and no. So I got 4 out of the 6 possible faces will be odd. Got it? So let's continue in the same way. Now let's say you removed a dot from there. There's 3 this time. 3 out of 21 is the probability that a dot is removed from that part of the dice. And if you do that, you get 2 dots remaining. So how many faces now have an odd number of dots? This one does, not this one, not this one, not this one, yes, and not that one. So 2 out of 6. So you're getting the hang of this, right? So I don't need to go through every single one here. So I'll just fill out the last 3. So far, if you've paid attention, you'll be able to do this on your own. For this one here, it is 4 out of 21, and the probability of getting an odd face is going to be 4 out of 6. For that one, it will be 5 out of 21, and if a dot is removed from there, the probability of getting an odd face is 2 out of 6. And finally, the last one, probability of removing a dot is 6 out of 21, and if you do that, probability of getting an odd face is 4 out of 6. But remember, this is a probability question, so expect a fraction. All right, let's see here. I think we can factor out the denominator, not necessarily factoring it, but just putting it in the bottom like that. And then everything else has the same denominator, so we can just concentrate on the numerators now. Got 2 plus 8 plus 6 plus 16 plus 10 plus 24. And that becomes 66 over 21 times 6. 66 divided by 6 is 11. So that's 11 over 21. And there you have it. So number 14, the answer is D. Let AB be a diameter of the circle and C be a point on AB with 2AC equal to BC. Let D and E be points on the circle such that DC is perpendicular to AB and DE is a second diameter. What is the ratio of the area of DCE to the area ABD? So, a little bit of labeling first. If 2 times AC is equal to BC, I will let AC equal X, and therefore BC will be 2X. So I'll put that somewhere in here, like that. All right? And then what else can I label? I can label the radii from this point. I'll call it O, or I'll call it C, I think. C. Well, C is already taken, so O is fine. That's going to be the radius, of course. And then from O to E is also the radius. Correct? And then this part here, from O to B, is also the radius. And so is from A to O. So what I'm going to do is I'm going to label this guy right here, O to C. And O to C is essentially R minus X. This guy right here. All right? So I think that should be enough for my labeling. If I need any more, I'll go back and label some more. Now, one thing I definitely need to draw is a line from E to meet the other guy, like that. And should I label it? Sure, I'll call it F right there. And now let's proceed with the question. They want us to find the ratio of triangle DCE, the area, to ABD, like that. Okay, well, DCE, we have 1/2 base. I can call DC the base. And the height I can call FE. And then for ABD, it's again 1/2 base, which is all the way from A to B. And the height is DC, right there. So you can see a lot of things cancel here. And when they do, the only thing I'm left with is FE over AB. So let's proceed now with trying to figure out FE and AB. Well, FE I don't know yet, but AB I do know, in terms of X at least. It's 3X, right? From here to here was X, and from C to B was 2X. So that's 3X. So if I can figure out FE, I put a little box there for FE. I think I should be able to solve this. All right, now how do I figure out FE? I'm going to look at two similar triangles. The first one is DOC, and it's similar to DEF. So here's DOC, and DEF is right here. And this ratio of the sides is therefore equal. DO over CO is equal to DE over FE, like that. So DO is the radius, CO is R minus X, based on how I labeled it. D all the way to E is 2R, and we got that over FE. So now we've got R, but we don't want two variables, right? We got R and X here, and that is not something that I want. I want one variable. Well, the entire diameter from A to B is 3x, right? Because from A to C is x, and from C to B is 2x. So 3x is the entire diameter. But the diameter is also represented by DE, and that I've labeled 2r. So 3x is equal to 2r, correct? So that means I can isolate for r and just get 3x over 2 like that. And that will help me a lot. So instead of putting r, I put 3x over 2. Instead of r minus x, I put 3x over 2 minus x. Instead of 2r, I will put 3x. And there you go, FE. So I've got everything in terms of one variable. So I got 3x over 2 minus x, which is x over 2. And this is 3x, and we got FE. All right, I think I can finish this on just one screen without having to scroll down. At this point, I will cross multiply like that is equal to 3x times x over 2. And then a lot cancels. The 3x's cancel from both sides. The 2's cancel from both sides. And then all I'm left with is just FE is equal to x. And therefore now I go back, I substitute my value for x as FE, or FE for x, or x for FE. And then the x's cancel, and all I'm left with is 1 over 3. And that's the answer to the question. And for number 15, 1 over 3 is choice C. Three circles of radius S are drawn in the first quadrant of the xy plane. The first circle is tangent to both axes. The second is tangent to the first circle on the y-axis. And the third is tangent to the first circle on the y-axis. A circle of radius r greater than s is tangent to both axes and to the second and third circles. What is r over s? So let's see if we can make this diagram just a little bit bigger. So here's the diagram blown up. And let's start labeling things and let's see what we can get. First and foremost, I'm going to draw a line from the center of the big circle down to the tangent point. I'll do the same all the way to the other tangent point like that. And then let's see here, how do I want to set this up? A line from the center of this little guy to the center there. One line from there to here, perpendicular. And I think that should be it. I think so. So this is, of course, a right angle. So draw that in there. And then if I were to label this, from here to here is S, right? Because it's the same as here to here. It's just the radius of that small circle. And then, let's see, from here to there, that entire way is the radius. So that means from here to here is the radius minus S. I hope that makes sense. And then from here to here, that's the radius of the circle, the large one. And then from the center of the small circle to that point is S, which is just the radius of the small circle. And finally, from here to here is R, correct? That's just the radius. And therefore, if you were to draw a line from there all the way to the bottom like that, that's also going to be R. But these three right there, if I were to draw a straight line like this, like that, that represents three S's, correct? S here, and S here. So this segment right here would be the R minus 3S. Okay, so that's the setup of the question. That basically creates a Pythagorean relationship in that triangle, this triangle right here. So what is that? It's R minus S squared plus R minus 3S squared is equal to this hypotenuse, which is R plus S. R plus S squared, like that. All right. Let's expand this. We got r squared minus 2rs plus s squared plus r squared minus 6rs plus 9s squared. And then on the right side, r squared plus 2rs plus s squared. Let's see, a few things will cancel. This r squared will cancel with that guy, s squared, that guy. And then I think that's it for canceling. Put everything on one side. R squared, minus 2, minus 6, minus 8, minus another 2, minus 10rs, plus 9s squared. And then, let's see, I hope this factors. R, 3 and 3, I don't think that will work. But how about 9 and 1? Minus, minus. Yeah, that should work. Yeah. So that means that r is equal to s or r is equal to 9s. Well, they tell us in the question, obviously, and it's pretty clear from the diagram, that r is not equal to s. So r must be equal to 9s. And if so, the ratio of r over s is just 9. And that's pretty much what they wanted in the question, r over s, right here. And therefore, the answer is D for number 16. A unit cube is cut in twice to form 3 triangular prisms, 2 of which are congruent, as shown in figure 1. The cube is then cut in the same manner along the dashed lines shown in figure 2. This creates 9 pieces. What is the volume of the piece that contains the vertex W? So here's the vertex W right there. All right, interesting question. This is that piece that they are asking us about right there. Well, that looks like a pyramid to me. And therefore, I can easily figure out the area of a pyramid, or the volume, sorry. Yeah, the volume, not the area. So the volume of a pyramid is 1/3 base times height. All right. Well, the base in this case is just a square like that. And this was a unit cube, correct? So that means this whole side is 1. So if you were to cut it in half like that, that means each of these sides is going to be a half. They don't tell you that the cut is down the middle, but they do tell you that 2 of the prisms are congruent, and that makes me conclude that this cut is indeed down the middle there. So the base is going to be just a square of side length a half. So its base area is 1/2 times 1/2. And then the height of this pyramid is basically from there to there, and that's just 1 since it's a unit cube. Each side is equal to 1. So there you go. So I got 1/3 times a half, which is 1/4 times 3, which is 12. And I believe that's it for this question. So number 17, the answer is A. Call a number prime looking if it is composite but not divisible by 2, 3, or 5. The 3 smallest prime looking numbers are 49, 77, and 91. There are 168 prime numbers less than 1,000. How many prime looking numbers are there less than 1,000? So we have to use a commonly used system known as the inclusion-exclusion principle. And this is done commonly in questions that involve trying to figure out how many numbers are divisible by something. You know, how many numbers are divisible by 4, how many numbers are divisible by 7 in a certain set. So in our case, they want us to figure out how many numbers are divisible by 2, 3, or 5, right? And then we have to subtract that from all the numbers less than 99. So I guess the numbers that are divisible by 2, 3, or 5 are sort of the bad guys, right? Because we want numbers that are not divisible by them. Okay, so first we figure out how many of the bad guys we have. We subtract those from 999, which is the numbers below 1,000. And then we take it from there. But it's not as simple as it looks, right? and I'll show you how. So the first thing you do is let's just figure out the bad guys. And in our question, those represent any number that's divisible by 2. So you take the total, which in our case is 999 numbers, all the numbers less than 1,000, and we divide by 2. And you take the integer value, that's what that symbol means. That will give you how many numbers are divisible by 2. Then we want how many are divisible by 3. Okay, 999 divided by 3. Then we do the exact same thing for 5. 999 divided by 5. All right, and that gives you basically how many numbers are divisible by 2 or by 3 or by 5. And this is 499, this is 333, and this is 199. Remember, we only want the integer values. And then you add these up. But the problem is it's not that simple because we have overcounted. There's a lot of numbers in here that we've counted twice. Which ones have we counted twice? Well, 2, 3, and 5 were the numbers we were interested in. We've counted twice numbers that are divisible by 6, which is basically 2 times 3. Numbers that are divisible by 10 we've counted twice, which is basically 2 times 5. And numbers divisible by 15 we've also counted twice. So we have to subtract those. So all the ones that are divisible by 6 we have to count only once. So since we've counted twice, we've got to subtract them. 999 divided by 6. And let's see here. Minus 999 divided by 10. And finally, 999 divided by 15. Okay, this takes care of the overcounts. So 999 divided by 6 is 166 minus 10. Or sorry, 999 divided by 10 is 99. And then 999 divided by 15, the integer value is 66. All right? Are we done? Well, not yet. Almost done. We've got one little thing remaining that kind of would be missed by a lot of people. And that's one additional part of the inclusion-exclusion principle. We're very close, but we're just one step away. We've also got to take into consideration all the numbers that are divisible by 30. All right? So 999 divided by 30. That has to be taken into consideration, and that is 33. Now here's the thing. These ones you have to add because we've taken too many of them out. All right? And if you are confused at this point, what I encourage you to do is try a smaller number. Instead of 999, try a number like, say, 35. Write them all out and do this manually, and then do the inclusion-exclusion principle. And you will see that this system works and why it works and that it makes perfect sense. All right? Okay, so now that we have this, let's figure out what this number is calculated to be. It's 733. So that means that of the 999 numbers, I've got to take away these bad guys, and that's 733. And that leaves me with 266 numbers that are not divisible by 2 or 3 or 5. But we also have to take away all the prime numbers. All right? Because we're not looking for prime numbers, we're looking for prime-looking numbers. Because those numbers have to be composite. And they help you out by telling you that there's 168 prime numbers less than 1,000. So subtract 168. Correct? But this question is a bit tricky because of the 168, we actually have already used 2, 3, and 5. Those numbers we've already eliminated up here, here, and here. One of those was a 2, one was 3, and one was a 5. So of the 168, we actually have to take these 3 out, leaving us with just 165. And that's tricky. And then it actually doesn't end there. There's another number we have to take out. We have to take out the number 1. Because that cannot be included, because the number 1 is not considered part of a prime looking category of numbers, because it's actually not considered a prime, but 1 is also not considered a composite. So we have to take that out. So if you do, you get 266 minus 165 minus 1, which is equal to exactly 100. And therefore, number 18, the answer is A. A faulty car odometer proceeds from digit 3 to digit 5, always skipping the digit 4 regardless of position. For example, after traveling 1 mile, the odometer changed from 000039 to 000050. If the odometer now reads 002005, how many miles has the car actually traveled? So the key is that you're always skipping the digit 4. So the digit 4 is never counted. And therefore, if we can figure out all the times the odometer shows a 4, we can subtract those from 2005 and we'll get the actual number of miles. Okay, so first let's remove all the digits with a 4 in the single digits. So the single digits basically means that you've got just one number here, and the only one that we are interested in removing is a 4. So there's only one way of that happening. So that's pretty simple, because when the odometer was 3, it doesn't go 3 to 4, it goes 3 to 5, correct? So single digits is easy, but what about double digits? When is it a double digit with a 4? Those are the ones that we are not going to count. Well, numbers like 14, 24, 34, all the 40s from 40 to 49, right? Because those have 4s in them. 54, 64, 74, 84, and 94. So all of these, since they have 4s in them, we have to not count them. So how many do I have? 1, 2, 3, 13, 14, 15, 16, 17, 18 of those. All right. And now we get into our 3 digits. Numbers that have 3 digits but have a 4 in there somewhere. Okay, it's a little bit trickier now. If you have a 3-digit number and the 4 is the first digit, that basically means any number from 400 to 499, and that's 100 numbers. So that's 100 numbers that we have to get rid of. Now we have to look at all the 3-digit numbers that are in other ranges. So for example, 100 to 199, all of these same numbers are going to be counted. So for example, 104, 114, 124, 134, 140 to 149, correct? 154, 164, 174, 184, and 194. So how many of those do we have? 1, 2, 3, 4. 4 plus 10, 14, 15, 16, 17, 18, 19. So 19 numbers that have a 4 in that range right there. And very similarly, all the other ranges will have another 19 in them. 300 to 190, 299 there. 300 to 399. Now the 400s we don't need to count because we already counted those. So 500 to 599 and so on. And each of these has 19 numbers that have a 4 in them. So the total for all of these guys is going to be, let's see how, 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 19, which is equal to 152. So I got 152 here, 100 here. So I got 252 there for the 3-digit numbers. And let's just circle these in red so that we know for sure which ones we're counting. And then the last one, of course, is the 4-digit numbers. The 4-digit numbers, in a very similar way, 4 digits, we've got numbers of that form, right? Now the first one has to be a 1. It can't be a 0. If it is, there won't be a 4-digit number. And the only 4-digit number that has a 4 in it is 2004, because we go up to 2005. So we got one number there. So we just need to be concerned about all the numbers from 1000 to 1999. All right? Now, we've got, let's see here, for a 4-digit number starting with 1 to have a 4 in this part of the number, the units digit, the 4 would be right there. And there's only one way of doing that. If we have a 4-digit number and the 1 is the first one and we want the 4 to go here, well, there's 18 ways of doing that. How do I know that it's 18? Well, I did it up here. And I did it over here several times. But I added 1 because of the 1 here. But if you just look at this one right here, double digits, it's 18. So I know that it's 18. And if I want a 4-digit number with a 1 here and a 4 here, well, I know that also. 3-digit numbers with 4 in it, it's 252. So 252 right here. Okay? So add 1, 18, and 252, and you get 272. All right, so this is really just a counting question. So 272, 252, 18, and 1. Those are all the bad guys. So 272, 252, 18, and 1. If you add up all of this, you will get 543. These are the numbers that have 4s in them, and we don't want to count them. So we had an odometer showing 2005. We have to subtract from it all the numbers that have a 4, because those numbers cannot be shown by this faulty odometer. So 2005 minus 543. And if you do that, you get 1462. And that is the actual mileage on the car. So number 19, the answer is B. For each x in 0 to 1, define f at x is equal to 2x if x is between 0 and a half, and 2 minus 2x if x is between a half and 1. Let f2x equal to f at x, and fn plus 1x equal to f at n at f at x. For each integer n greater than 2, for how many values of x in 0 to 1 is f at 2005x equal to a half? Okay, a lot in this question here. Let's try to understand it. First and foremost, I want to draw a graph of this so I can get a clear understanding of what it is I'm dealing with here. So let's draw a simple graph, nothing fancy, and let's see what we get. So I've got f at x, and I've got x, and my interval is from 0 to 1, right? So I'll just work within that interval. I'll use 0, I'll use 1, I'll use a half, and let's use something in between, a quarter and 3/4. I think that should be sufficient to draw this graph. So here's my x-axis, here's f at x, and here we go. So when x is 0, which one do I use? This one or this one? Well, look at the ranges. X is 0, it's in this range, so I'm going to use this one. If x is 0, it will be 2 times 0, which is 0. Correct? I just plugged 0 into there. How about a quarter? Still going to use this one, so it's 2 times a quarter, which is a half. a half. Okay, be careful. A half is tricky because x is equal to a half here. X is not equal to a half here. It's greater than a half. So you're still going to be using this one. So a half for x, 2 times a half is 1. 3/4, now we start getting into this guy here. If you substitute 3 over 4 into this equation, you get 2 minus 6 over 4, which is a half. And then finally, if you put 1 into there, you get 2 minus 2, which is 0. Okay? So now we can plot this here approximately, let's say, like that. This is being a half, 1 3/4, and a quarter. And on the f at x graph, quarter, a half, 3/4, and 1, approximately. Okay, let's start plotting these values. We got 0 here, 0, 0, a quarter and a half, so approximately there. Half and 1, so that's there. 3/4 and a half, that's there. Oops, not there. Here. And then 1 and 0, so right there. All right, let's join these lines up, see what we get. It's going to be approximately like this. It's not perfectly drawn to scale, but so there's my graph for f at x. Okay, now we want to know, when is f at x equal to a half, right? Because I'm going to extrapolate later on. This is 2005, but I obviously have to start somewhere. So I'm starting just with f at x. When is it equal to a half? Well, a half is here. Okay, that's where a half is. I'll just label them just to be, complete here. That's 1, and this is going to be a half right here. So when is f at x a half? What is the value for x? Okay, no problem. Just draw a line from a half across, like that. And wherever that line intersects, that will be my values for x. And in our question, we actually figured that out. F at x is equal to a half when x is equal to a quarter and 3/4. Okay, so how many values? It's 2 values. So far so good, nothing complicated, right? Okay, so we're going to do this again. I'm only going to do it once more because I want you to actually do other values on your own. I'm going to do one more, but this time for f at 2x. Okay, so here we go. This is the second graph. So here we go. We are now figuring out values for f at 2x and x. And in a very similar way, I'm going to do it only for our range, 0 to 1. I'll put a half, I'll do a quarter, and I'll do 3/4. Okay, so if I plot them, it'll be a half, a quarter, 3/4, and a half, approximately like that for x. Okay, here we go. So how do I do this here? Well, I use this formula right here. They've given it to me for f at 2 at x. So f at 2x is equal to f at x. All right? So here we go. For the first one, 0. When x is 0, we've got f at 2, 0 is equal to f at 0, like that. Okay, well, x is 0, so I'm going to use this equation. When x is 0, we have 2 times 0, which is 0. So this becomes f at 0. Correct? X is 0, so you look at this part of the equation. This is the range. X is 0. Use this formula. You plug x equals 0 into there. You get 2 times 0, which is 0. And therefore, f at 0 is 0. Okay? Now we have to figure out f at 0. Well, in the same way, f at 0 is 2 times 0, which is 0. Okay, so that goes there. 0 goes there. Okay, so we're done that one. Now let's try f at a quarter. F at 2 a quarter, like this. Okay, that's f at a quarter, like that. Well, which formula do I want to use? X is equal to a quarter, and that's in that range, right? So I'm going to use this one. So f at a quarter is 2 times a quarter, which is 2 over 4, which is a half. So this becomes f a half, like that. Okay? And then f at a half, it's this range. So again, we're going to use this guy. So f at a half is 2 times a half, which is 1. Correct? So this is 1 right here. All right, so I hope you're following. We're going to do 3 more, correct? F at 2. Now this time we're doing a half. So we got f at a half, like that. And f at a half, we're still in this range actually. So 2 times a half is 1. So now we have f at 1. And now finally we get to use this guy, because now x is 1 and we're in this range. F at 1 is 2 minus 2, so that's 0. So there you go. That goes there. We got 2 more. I think I can squeeze this in. F at 2 3/4 this time. So we got f at 3 over 4, like that. F at 3 over 4, we're going to use this one here. So 2 minus 2 times 3 over 4. So that becomes 2 minus 6 over 4, which is a half. So this becomes a half. And then f at a half, we use this guy, and therefore that's 1. So this becomes 1. And then finally, squeeze it in here, the last one, 2 f at 1. So this becomes f at 1. We use this one, so that f at 1 would be 0. So we have 0, and then f at 0, you just use that one, so that'd be 0. So there we go, we got it. So this won't be drawn to scale, but I can put in the values. 1 will be, a quarter will be 1, say approximately, let's see here, quarter, a half, 3/4, like that. So approximately there. 1/2 is 0, 3/4 is 1, and 1 is 0. So the graph this time looks like this. We got from the origin there, down to there, then to there, and then back down. So now if I asked you the question, when is f at 2x equal to a half? Our famous a half, like right there, they keep asking us. Well, in this case, you draw a line from a half, which is here, right? You draw a line, and that would be like this. So how many x values do you get this time? Well, you get 1 x value, 2, 3, and 4. All right? 4 x values for f at 2x equals a half. So how many do we get for f at x? We got 2x values. So for f at x equal to a half, number of values of x, we got 2. Remember? This was 2 right here. And then for f at 2 to the x is a half, we got 4 values here. 1, 2, 3, 4. And what I would like you to do is just do a couple more. F at 3 at x, if you can bear it. and you'll see that is 8. Basically what it means is that it doubles every time. So this is 2 to the power of 1, this is 2 to the power of 2, this is 2 to the power of 3, correct? So if you extrapolate that all the way to our requirement, which is f at 2005x, f 2005x is equal to a half, that will be 2 to the power of 2005. And it's some obviously very big long number of values. So this is our answer. So it's a challenging question. It's a difficult question in my opinion to first understand and then do quickly on a math contest because you have a limited amount of time. But if you can come up with some shortcut or a different way of analyzing this, then that's wonderful. So 2 to the power of 2005 would be choice E.